So let's having look at how these things look like in the actual computational model. Let's in this video talk about or give you a big picture of how finite element analysis work in practice. Now, I specifically record this video as a separate one just for this slide, so you can go back to look at this slide very often to understand, where does individual parts sit in the whole process. Now, the whole finite element analysis is broken down into a workflow that we call the stiffness methods. Now, this works because we are treating everything linearly. Now, that means when you apply a force to the material, they will deform linearly. Okay, this is what we're gonna focus in our course. Of course, when the finite element analysis gets more and more difficult, it goes into a non-linear regime. That made the whole thing more complicated, which we're not going to be talking about in this class. Right? So how does the stiffness method work? Well, you first start by discretizing the whole structure. So if you have a continuous body, you need to chop it down into individual parts, right? And typically, people say in finite element analysis, everything is a triangle because triangle is the most often components that people use to discretize the structures, right? Now, once you got each element for the whole structures, you need to work out equations that determine the relationship between the force applied to the structures and how they deform, right? And typically, we do or establish those equations on what we call the node or the boundary points on each of the elements. So if you think about a triangle, there are 3 points at the corners, so those are the nodes. So that's what I mean by determining the equations for each element in the matrix form. And then you need to put all these equations on the individual node into a global coordinate system, right? What does that mean? Well, if you break down individual triangles, right, you can work out how the force is going to move, how the displacement going to move. And that's typically done in the coordinate system of that one little pieces, right? But when you put it back together, the whole structure, for example, a whole bridge sit in his global coordinate system, like X, Y, Z for the whole bridge. So you need to transform those individual nodal equations into the global coordinate system, so become consistent, right? And once you've done that, you got all the equations in hand, you put them into what we call a matrix, right? If you do your first year mathematics, we all know what matrix is, right? In a very simple word, that matrix just look like a Hooke's law, where your F now become a long vector of all the forces on each node. F equal to K times X. K is what we call the stiffness matrix. We'll talk about it later. That's why it calls the stiffness method, right? What F equal to K dot X. X is basically the displacement on each individual node. So you put all of them in the matrix form, right? That allows you to solve for the displacement of the whole structures, right? When certain nodes are being applied to certain forces, right? We'll see some example how that's done, right? Once you know how different part of your structure displays under the forces, we can also work out what's the actual force at those specific nodes that drive that displacement to happen. So this is basically the whole, the high level overview of what we try to achieve using finite element analysis.